Okay, I think it's time to start. So welcome to this online webinar organized by ANIPH and MAGICBIOMAT projects. Before we begin, please note that this session will be recorded. We kindly ask you to keep your microphones muted during the presentations to avoid any background noise. And if you have any questions, please write them in the chat and we will address them at the end of all the talks. In this session, we will explore how 3D printing and biofabrication are opening up new opportunities for the development of bio-based and biodegradable materials with enhanced circularity and reduced environmental impact. As sustainability becomes a key driver of innovation, additive manufacturing is creating new possibilities for design high-performance materials while also considering their end-of-life management. Through the webinar, we will look at applications across sectors such as healthcare, packaging, and advanced biomaterials. We will also gain insights into the role of artificial intelligence in material design, as well as emerging approaches to program biodegradability, which are helping to shape the next generation of circular and sustainable materials. Our first presentation is going to be by Juan Antonio Marchal Corrales. It is titled Sustainable Bioinks and 3D Bioprinting for Personalized Medicine. Professor Marchal is a full professor of human anatomy and embryology at the Faculty of Medicine of the University of Granada, and a principal investigator of the BioFab in I3D laboratory for biofabrication and 3D bioprinting. His research focuses on regenerative medicine, cancer stem cells, nanomedicine, biomimetic materials, bioinks, and 3D bioprinted models for precision medicine. He has led and participated in numerous national and international research projects, is inventor of several patents, co-founder of technology-based companies, and has an extensive scientific track record in biomedical research. In his presentation, he will introduce current strategies in 3D bioprinting and biofabrication for the development of biomimetic tissues, advanced bioinks, and disease models. Special attention will be given to medicinal application in regenerative medicine, cancer modeling, and personalized therapeutic approaches. So, Juan Antonio, the floor is yours.
Thank you so much, Anna. Thank you to Icon and Sofia for organizing this webinar, and also to Anna for the presentation. I'm going to share my screen. Now you can see it better. Full screen. You can see my full screen.
Not at all.
Not at all. Sorry, one moment. One moment.
I think if you click, yeah, perfect. Thank you.
Now, thank you so much. I'm going to start. We will have time to respond to all the questions at the end of this webinar. As previously said, Anna, I'm Juan Antonio Marchal. I'm a full professor in the Faculty of Medicine and the director of the biofabrication and 3D bioprinting laboratory, circular laboratory in the University of Granada. My talk is related with the use of sustainable bioinks and the application for 3D bioprinting. I will show you some of the results we have in our laboratory and some of the advantages that have these natural and sustainable bioinks. My first slide is related with the how we are currently living in the era of the precision medicine. That means that, for example, you can see here in the table in the scheme how in the USA the 10 highest grossing blockbuster drugs fail to help a large fraction of patients. You can see here in blue the person that they ask of help for these people. But also, do you have in red the people that in the condition of that this drug fail in improve the disease, and they are of between 3 and 24 people. This mean that the one-size-fits-all treatment are not cause no benefits to the patient and are the reason of several secondary effects and costs for the sanitary health systems. And that now, in the last year, there are some changes related with this, mainly a paradigms shift for this imprecise medicine toward precision medicine, that is a more holistic view of an individual patient, and is related to the direction toward a more personalized medicine. In the column of the left, you can see the classical one-size-fits-all medicine, in which you can see the patient that are with a treatment. This treatment provoke not only benefits for this patient, but in several patients, cause adverse events, as previously mentioned, or it doesn't benefit for the patient. Now we can move from the toward an stratified medicine where the patient are grouped by disease type, by demographic, socioeconomic, clinical feature, and biomarker. We can have molecular subpopulation using several genomics and omics technologies. Also, we can have a record from the patient in the lifestyle, the preferences, all the health story along the time, the medical records, and also even we can have the exogenous factor. And the final goal is to have this precision medicine that what an individual patient, in combination with the companion diagnostics and therapy, we can have as a result that each patient benefits from individualized treatment. In fact, this precision medicine ensures the delivery of the right intervention to the right patient at the right time. And then in this case, we have the 3D bioprinting that can have the same philosophy of this precision medicine. We can use this technology to have a more precise and personalized medicine. On the left, you can see here how the cell therapy is personalized. You can obtain a biopsy from a patient. This biopsy, you can isolate the cells, have this cell in cell culture, and then use the proliferation of this cell. And after you mixing with the cell-specific scaffold, because the injuries of the tissues are in 3D, you can mix these two factors, the cells, proliferated cells, and the scaffold, and using several growth factors or mechanical stimulus, you can have a mimetic tissue that can be implanted again in the patient, in the patient. But using this technology, the 3D printing technology, the workflow is different because we can obtain several kinds of cells from a biopsy. For example, in this case, are represented the cell obtained from the skin. For example, we can obtain keratinocyte from the epidermal layer, melanocytes also from this epidermal layer, fibroblasts from the dermal layer, and also we can have some biomaterials and biomimetics inks that can be used to obtain the bioinks. The bioinks are a mixing of the cells together, this biomaterial, biocompatible biomaterial that can be introduced in this 3D bioprinters system, and also to have a more precise, and using this additive technology, similar to the 3D printer, to have a complex tissue with several kinds of cells, with several layers, and reflecting the real structure of the tissues and organs. We can maturate this constituent using bioreactor and then to implant in the patient and the results are better than if you use only this specific approach that was used in the last years. 3D bioprinting has several advantages, such as the unprecedented precision, the automatization, the scalability and the standardization, the good cost effectiveness. We can use several different bioinks and different cell types in the same bioink or in the same process of 3D bioprinting. And also we can not only use this 3D bioprinting for regenerative approaches, but also we can use this for obtaining detailed tissue model that can be used for transplantation, or even in vitro to for example, to have to try new drugs or to have a detailed model of disease in vitro. Okay. In this case, why we can use sustainable bioinks? Because we have several needs. A scientific need, use these sustainable bioinks to support the cell viability. As you can see here, they need to be compatible, biocompatible, support the viability and tissue-specific function. Also, we have environmental needs because this material can generate waste obtaining from natural waste products. This biomaterial can be used and they can have a high reagent use and also we can have a more efficiency in the use of the sustainability in the future. Also, we have a translational need because in the case of regenerative medicine, we need to have a scalable, reproducible, and safer biomaterials to improve the application, future application in some disease that have not a good therapeutic approach at the present. And also we can have this specific biomaterial that can be used for industrial adoption and commercialization. And also we have an opportunity, the circular economy. This renewable material and polymers. In the case of ANIPH, we have some polymers that have this main objective. And also after Anna will explain the projects, and also the valorization of these bioproducts. And this is important. They can create a high value in the economy. Next, and what is a sustainable bioink? A sustainable bioink is a cell biocompatible bioprinted biomaterials that can be renewable and obtained from waste-derived sources. Is biocompatible, can be printed, and also is tunable in the mechanical properties. Also, the characteristics of this sustainable bioink that they have low toxicity processing, are biodegradable, and are scalable and reproducible. This is very important, and this is a very important need for the future clinical applications. Which are the main criteria for a good bioink? We have the two criteria. The main criteria are the printability and material performance, and the other is the biological performance. In the case of the printability, they need to have to have several good properties, such as the viscosity and surface thinning, the gel strength, the filament fidelity, the maintain the shape, retain the shape after 3D bioprinting, and they have good kinetic cross-linking properties, and also the swelling, degradation, mechanical stiffness that are important for to have the 3D structure and to mimic the specific tissue we need to regenerate or to improve the properties. And also we have some requirements for the biological part, such as they need to have able to have the cell viability after printing. They need to increase the proliferation of the cell over time, maintain the morphology and spreading, they can improve the differentiation or maintenance of the phenotypes we are of the kind of cell we will use, and they will need to have or to produce extracellular matrix in an adequate manner, because the extracellular matrix is very important for the tissue to maintain the 3D structure and to maintain the differentiation of the cell and the proliferation, and also avoid the inflammatory or cytotoxic response from the body. And as summary, a successful sustainable bioink must satisfy all these printability properties and the biology characteristic. There are several biomaterials that are used for 3D bioprinting. Here you can see in the top part of the slide the natural biomaterials that are sustainable, such as the collagen, the hyaluronic acid, the gelatin, the agarose, fibrin that is obtained from the own patient and from the blood of the patient, and also the alginate. You know, all these materials that are in the foods with several applications, but also it's important to have other materials that have, because when you bioprint a structure, you need to maintain the structural fidelity, and sometimes depending on the tissue, we need to the goal of the tissue we need to print. We need to use some other material. For example, here you have some polymers that are not from original natural origin, such as the polyethylene glycol, the polylactic acid, or the polychloroplankton. These materials are not natural, but they improve the structural fidelity of the 3D printed hydrogel or scaffold. But also, as in ANIPH project, we need to develop new biomaterial that can be sustainable. And then also, Anna will explain in the next talk the characteristic of ANIPH projects. Which are the main sustainable biomaterial families? In these families are mainly plant and algae-derived polysaccharides, such as previously mentioned, alginate, pectin, agarose, and some other material. The main strengths are that they are renewables, they are abundant, and also biodegradables. In the other part, we have a challenge, the need of improve the rheological properties and tanning properties, and also the biofunctionalization to improve the proliferation and maintenance of the differentiation of the cell. Also, we have nanocellulose system, or a mixing of the pectin and cellulose blends in the frame of the project ANIPH. We have some cellulose that we will use for improve the property of the biomaterials. They have some strengths, such as the excellent reinforcement of the structure, the self-cleaning control, and there are some challenges, such as the limited intrinsic bioactivity. And in the case of the mixing of the pectin and cellulose blends, we have some challenges, such as the formulation optimization required to have several rates each material, and some strengths, such as the improved print fidelity to have this 3D structure. Also, we have some sustainable biomaterial obtained from marine products, such as the alginate, chitosan, carrageenan, or fish gelatin. They have a fast gelation and broad availability as a strength, and some challenges are the problem with the cell adhesion in this kind of material. And finally, we have some specific results from our lab related with this part. These are the cell-derived, the cellular extracellular matrix biomaterials. This cell-derived, the cellular extracellular matrix is obtained from the human, from the patient, or from the a person, sorry, and we can obtain the cell from the person. We can have, for example, cell-derived extracellular matrix from mature cells, such as you can see here. We can obtain this from fibroblasts, for example, for skin application, or even mesenchymal stem cell obtained from for example, from lipoaspirate, we can obtain a small biopsy of the tissue and then obtain the mesenchymal stem cell, proliferate this cell, and also obtain some specific extracellular matrix adapted to the specific tissue we need to help, no? And also we can obtain the fluoride cell sheet or even from tissues or from organs, use this fluoride tissues or organ to use as a specific biomaterial for 3D bioprinting. The production workflow is we obtain the cell, we expand the cell, induce the cell to produce this extracellular matrix, and after we introduce the cellularization process, the solubilization and formulation of the bioink, and then the printing and the bioprinting and cross-linking together the cells. Some strengths are the human relevant bioactive cues, because we have in this extracellular matrix, we have some factors that are produced by the own cells that induce the maturation of the cell will be used for the 3D printing process. Also, we improve the compositional control. We have a better reproducibility than tissue-derived extracellular matrix because the availability or the amount of this organ-derived or tissue-derived matrix is low because we are from human origin. In this case, we can proliferate the cell and have a lot of cell to produce this matrix, and also we can have a big amount of these biomaterials. And also another strength is the tunable and compatible use for personalized medicine. Some challenges is the low matrix yields. It's a problem, but using bioreactor we can improve this. The longer production time, we need to have time enough to have enough amount of this extracellular matrix. The cost and scale-up possibilities, and also the donor. No, the donor we need the cells, but when we have the cell, we can proliferate this, and there is a few problems. And also the standardization. This is a problem for the clinical use, the future clinical use. And the next is there are several kinds of 3D bioprinting system. For example, the extrusion-based 3D bioprinters that use a pneumatic pressure piston or a screw. The inkjet printers that use heater in these syringes or a piezoelectric actuator to obtain droplets with the bioinks. The stereolithography-based 3D bioprintings that can you see here? And here we use several pulse laser and lens to obtain a photogravable resin and produce the 3D structure. Now for the application, do you have here the process for 3D printing of the tissue? Firstly, we can obtain we need to obtain the image using several diagnostic image techniques for a specific organ injury from the patient. Then we need to do the design of the 3D structure. We need to 3D printing, and also they use the specific biomaterial, as previously mentioned, to select the specific cell, mature cell, or even mesenchymal stem cell, or even induced pluripotent stem cell. And the next step is the 3D printing, bioprinting, using the several techniques previously mentioned. And the final step is the application, while using a bioreactor for maturation of the 3D tissue, or even the direct implantation in the injured tissue. And also, finally, we can use this 3D printer structure for in vitro testing of drugs, etc., or to analyze the behavior of this 3D structure, the cell, etc. And now we will have some examples of this application in our lab. As you know, I will start with the skin. The skin is a tissue that is injured for several factors, such as burn, or for example, in specific disease conditions such as the diabetic foods, etc., or from surgeries or tumor processes, etc. And depending on the degree of the skin injury, we have several deep of these injuries. And in this case, the main gold standard is the treatment the patient is the autograft from the own patient. You need to obtain a skin from the other part of the body and then use for a specific the specific lesion in the patient. But the problem is the insufficient, which we have large areas or more several wound areas, because we don't have enough amount of this autograft. And also we have several products in the market that such as a cellular skin substitute, but they not fully are functional or have a multi-layer structure. In our case, we have developed a specific biofabrication. It's the BT skin is biofabricated three-layer skin, and in this case, we have used some natural biomaterials, sustainable biomaterials, such as some of them is based mainly in collagen and agarose, and also in each layer we have the idea was mimic the composition of each layer in a normal skin tissue. No? In this case, we use collagen 1, keratin, and sphingolipids. In the case of the epidermis, that is the surface layer. In the case of the dermis, we use fibroblasts. The cells are here, keratinocyte for the epidermal layer, the fibroblasts for the dermal layer, and the mesenchymal stem cell for the hypodermal layer. And in each layer, we use the specific component. For example, in the dermal layer, that is the main responsible of the elasticity and the regeneration property of the skin. We introduce the collagen 1, the hyaluronic acid, the dermatan sulfate, and elastin in this layer. And in the hypodermal layer, you use this collagen 1, hyaluronic, and dermatan sulfate. And here you can see some specific experiment we did. The first experiment were to demonstrate the gelification property of the bioink. This bioink, you can see here for each layer the viscosity, and this tube inversion test to demonstrate the ability to form a gel, and the mechanical property. We studied the mechanical property. After that, we did this specific geometry for the 3D bioprinters with this specific dimension, as you can see here, and then and this pore and geometry. And you can see here in this image, the photography at the first day with the hydrogel with the 3 layers. After 2 weeks, you can see here we have conserved the geometry of the hydrogel, and the cells were alive inside this hydrogel. After we can produce several kinds of this hydrogel. Also, we can lyophilize this hydrogel without cell and reconstitute to obtain this specific structure. And also, we can adapt this to produce scale up this hydrogel to obtain chip directly to put in the wound of the patient. No? Here you can see confocal microscopy images with the cell in each layer of the hydrogel. In green, in this epidermal layer, you can see the keratinocyte, human keratinocyte obtained from the biopsy and put in this hydrogel. The dermal layer with the fibroblasts, and the epidermal layer with the mesenchymal stem cell. And also we did the experiment in the animal, in a specific model of skin injury. This is in mice. As you can see here, we have several groups. The control without any application, the autograft from the same animal, and our hydrogel with cells. And after 2 weeks, we observe in the evolution of this wound that we have a significant result about the wound scale area after 2 weeks that were more significant than in the gold standard, the autograft. And at the end of the process, as you can see here, you can observe that at the end of the process, we have a perfect wound healing in the animal. Okay. In relation with the cell-derived, the cellular extracellular matrix for 3D bioprinting, the process we obtain sample from from lipoaspirates in patient. We isolate the mesenchymal stem cells that are stem cells that have some property of differentiation toward several tissues. In this case, for application we have some several applications. After the proliferation and differentiation and characterization, we induce this process of decellularization. We have the gelification of the bio-ink, and then they use for the 3D bioprinter. In a specific application for cartilage, you can observe here that using this mesenchymal stem cell, adding to the TGF beta 3, we induce the pre-differentiation of this mesenchymal stem cell toward cartilage tissue. This is the demonstration here in the C figure. You can observe how the staining of this cell in culture are similar to the chondrocyte, that are the cells that are obtained from the cartilage, mature cartilage. You can observe the increase of collagen 2, the glycosamine glycans as in the cartilage, and also the aggregate that is a marker of differentiation toward cartilage. Also, you can see here a graphic in the quantification of the collagen 2 is the main indicator of differentiation of this cartilage, of this mesenchymal stem cell toward cartilage. And after this, these are the matrices with the staining of the specific staining for cartilage, pre-decellularization, and after the decellularization, you can observe that all the matrices maintain all the main components that are such as collagen type 2, glycosamine glycans, and also we did a proteomic analysis with the several collagen we have inside, and we demonstrate that inside this extracellular matrix we have proteins that are important in the cartilage, in the extracellular matrix of the cartilage. Then we have the power, lyophilase power with our matrix. This power can be used, ready to use when we need, for example, for application in the patient. We did this gelification process, and you can observe that we obtain a gel that can be extruded by the 3D bioprinters. Here you can see our filament in this image of the scanning electron microscopy with several concentration of this decellularized extracellular matrix. And after that, we did this 3D bioprinting in an scaffold, because for cartilage we need an scaffold, and put this scaffold in a pocket in the mice, a subcutaneous pocket in the mice. And after 1 month, you can observe here that we obtain after 4 weeks, 1 month. This is the cartilage, the structure of the cartilage. We obtain this sample from the mice, and you can observe that all were able to maintain the cartilage properties after these 4 weeks in the mice. Another example. Sorry, I'm rolling with the next slide. Sorry, I'm going to share again. Another example that has been published analysis from our group is the use of IPS, induced pluripotent stem cell, obtained from omentum from a patient. They obtain this IPS cell, and also they obtain the extracellular matrix from the tissue, and they generate a nitrogel, use this decellularized extracellular matrix, and from the IPS they induce the differentiation toward cardiomyocyte and endothelial cells that are responsible for the vessel in the heart. And they did a bio-ink composed by this extracellular matrix obtained from the own tissue from the patient, and also using a gelatin as sacrificial bio-ink, and they did the bio-ink formulation and did the 3D bioprinting of the cardiac patch with the 2 kinds of cells, and also a hair-like structure, a complete hair-like structure. Here you can see the result. They obtain a mini hair with the same property of the same, using an image of this patient, an eye image of the hair of this patient, they were able to bioprint this alive 3D mini heart. The mini heart don't have the ability to contract of contraction, but you can see here in this image, real image, nor colored images with a specific marker for each kind of cell, the cardiomyocyte in this color, and also the endothelial cell in orange, producing the vessel and all the cavities of the hair. This is an example. This mini hair can be used alive for to try to test several drugs, toxic drugs, new drugs, and analyzing the toxicity, or to do a personalized medicine with a specific treatment for this patient, for example. Another example is for the application in the skin for skin regeneration. We are using this extracellular matrix obtained by from fibroblasts, from a biopsy from the skin of a patient. We proliferate the fibroblasts and also the mesenchymal stem cell. And to do the bioink, we use the human plasma from this patient. We obtain this the fibrinogen, and we obtain this bioink. We have the ability to using thrombin to do the gelification of this bioink. And the idea is this: we obtain an image of the injury of this patient. In this case, is a venous ulcer. We a 3D scan. After that, we obtain this 3D structure, and we use the extracellular matrix obtained from the fibroblasts. And after that, we mix with the cell, and the results are this. This is some results from the specific application in this patient. You can observe here a venous ulcer in this patient. We put this marker to obtain the 3D image using this 3D scan system, and from the several venous ulcers of this patient. After that, we obtain the mold of this injury, and after we bioprint. I have problem with the video, but this is the bioprinters with the two components of the bioinks with the cell, and after the 3D bioprinting, we have the specific shape of the lesion of the injury, and with the cell inside at the same time. And the idea, and this now we are working in this consortium. It's a network in Spain, financed by the Ministry of Health. That is now we are trying to prove this in a GMP facility to do a clinical trial in the next year. And this is the main future direction and research opportunities in the 3D bioprinting using this sustainable biomaterial. It's important the use of artificial intelligence to guide in the optimization of the bioinks, as you can observe here. And also it's important the use of these several waste products, for example, or in the case of the human origin, we can use the cell and induce this production of the extracellular matrix can be considered as sustainable bioinks. And also we can combine several sustainable bioinks to improve the property of this in the 3D bioprinting. And also we can the main challenge is the standardization of this bioink for application in patient in the future. And also the several applications we have several applications, such as I previously showed, such as the cartilage, the skin, the wound healing, for in vitro disease model, and other applications in regenerative medicine. And finally, as conclusion, the most promising part is not just greener material, it is sustainable performance. Finally, this is my research group. This is the most important of all my presentation, because we have several profiles in the research group. We have biomedical engineers, biologists, pharmacists, mathematics, etc. And this is important, the collaboration between the several fields of science to have the result, because the patient waiting solution. Thank you very much for your attention. This is all.
Thank you very much for this detailed presentation, Juan Antonio. It's really interesting that many of the materials currently available in our body can be used with a 3D printer. And just a reminder for all the attendees, if you have any questions, you can ask them via chat, and we will answer them later. Our second presentation of today, titled Sustainable Probiotic Functionalized Wound Resins from Bio-Based Design to Control Biodegradation, will be delivered by Ana Voltes Martínez. Ana holds a bachelor's degree in health engineering from the University of Sevilla, as well as a master's degree in tissue engineering and advanced therapies, and in biomedical engineering and digital health. She's currently developing her doctoral thesis in the biomedicine program at the University of Granada, within the research group led by Juan Antonio Marchal. Her work as a research and development scientists focus on new biomaterials and their effects on different cellular processes at macroscopic, cellular, and molecular levels. She also has extensive experience in digital design, modeling, and 3D bioprinting. In this presentation, she will explain the development of PHBB-based wound resins functionalized with probiotics. PHBB is a bio-based and biodegradable plastic that offers a promising alternative to conventional plastics used in healthcare. By integrating probiotics, these wound resins aim to support wound healing, reduce dependence on antibiotics, and enable control and environmentally friendly biodegradation. Anna, wherever you want, the floor is yours, and we can see your presentation in full mode. Thank you.
Thank you, Anna, for the presentation. Can you see my screen?
Yes.
I think, okay, perfect. So good afternoon to all. My name is Ana Voltes, as Anna said before. I'm a researcher at the University of Granada in the group of led by Juan Antonio Marchal. Now I'm going to talk briefly about the ANIPH project. That is, ANIPH is the acronym of Avoiding the Negative Impacts Produced by Plastic Materials in Humanitarian Context. And specifically, I'll be discussing about the development of sustainable probiotic functionalized wound dressings. Oh. Okay, now, sorry. Well, as many of you already know, there's a serious problem with the use of non-reusable and non-biodegradable plastics. One of the sectors that is affected by this problem is the healthcare sector, where in addition to the plastic waste, the biological waste is also generated. So this can be a public health problem in a future because of can provoke resistance to some treatments in relation to diseases. So what is ANIPH seeking to promote? Well, ANIPH wants to prevent the negative impact through the use of bio-based and biodegradable plastic products. To do that, we are developing bioplastic materials derived from polyhydroxyl canoates, or in this case, PHBB, as I mentioned before, that are based on all the project is based on a circular economy strategy with controlling the biodegradation properties of the materials. In ANIPH, we are focused on the biofabrication of the sustainable wound dressing and its packaging, also its packaging. So briefly, this is a summary about the specific objectives of the project. And the first step is the development of our future, in the development of our future projects, the synthesis and the production of the PHA-based materials. that they have to maintain while maintaining their specific properties. So we have to modify a bit the formulation and the compounding process, so that will improve the processability and the future biodegradability of the material. That is our focus, no? And besides, at the same time, we are developing a bioactive, antibiotic-free material based on probiotics and bacterial cellulose. This will help to prevent future infections in open injuries. So these materials will be combined to produce those sustainable wound dressing. And well, the PHBV together with the probiotic cellulose will be used for the wound dressings, and PHA, that is another PHA derived material, will be used in the manufacture of the packaging. All of this will ensure the safety and zero ecotoxicity of the final product. And during the whole process, we'll also use an AI tool. We'll use an AI tool developed by the Agricultural University of Athens that is capable of predict the product's behavior and the degradation capacity in different environments. For example, in different kinds of soils or kinds of water. Okay, so what do we need to design those wound dressing? Well, first of all, we'll need the PHBV materials combined with the probiotics cellulose. So we have to adapt them because by themselves they are not extrudable, no? Because we want to use them in with 3D bioprinting techniques. Why? Because we want to personalize the design of those wound dressing and adapt them. Depends on for example, the injuries of the future patients, no? So it's important to remark that those materials are not mixed. They are combined because they have different mechanical and physicochemical properties. So they are combined like layer by layer, in a layer by layer bioactive structure. So once we biofabricate the wound dressing, we always have to characterize and validate those bioactive wound dressing to demonstrate that they are safe, non-toxic, and that they can help to, in this case, to prevent the infection in open wounds. That is our goal. So now I'm going to show you some few results, previous results of the project. Well, on this slide, we can see the result. The left side is the product. It's bacterial cellulose. Okay, that will be the base of our probiotic cellulose product. In the right side, on the image of the right side, sorry, you can see a scanning electron microscopy image that shows you like the combination of the probiotics. Can you see the arrow? More or less. Well,
Yes.
here we can see. Okay, thank you. Here we can see the probiotic material that is combined. In this case, is combined or inside the cellulose fibers. And in this slide, we can see another result of the biological characterization of the product. We can see fluorescent images. We can see here green and red dots, no, more or less. They represent in green we can see live cells, okay, and in red we are seeing dead cells. So what we want to show you with this slide is that we are generating like a living material, no, that is capable to interact with the environment. Okay, and the manufacture technique of that we use in ANIPH is the 3D bioprinting. With this process, we can produce the 3-dimensional structure, no? using the material. We can use natural or synthetic origin materials, but in this case are all from natural origin. It's great because we can combine materials with different viscoelastic properties. We can vary the physical and chemical requirements. We can use, for example, in this case, the probiotic cellulose has a completely different properties compared to the PHVB material. The PHVB material is a polymer. We need to extrude it using thermal treatments. We can, as I said before, we can combine them thanks to the 3D bioprinting techniques. The design is previously created using CAD software, so it's not really complicated. We just need to adjust the model to the reality, no? In this case, the injury. After the generation of the wound dressings, we have to validate the products obtained and with a deep characterization of them. So we perform, well, the first of all is establish the printing properties of each material. This is something in those materials that has never done before. And we determine their mechanical properties after the process. So in this case, for example, we prefer, or we want the material is flexible, as you can see in the video. We'll also have to check if the material is still safe, that the thermal treatment doesn't affect at all on the wound dressing, that is still biocompatible and non-toxic, because it will be in direct contact, no, with skin in this case. Of course, together with the whole project is focused on the biodegradability of the material. So we also want to check, no, those properties. Well, and these are just, well, the first prototypes of some bioactive wound dressing. You can differentiate the PHVB structure, is like the squared structure, and together with the probiotic cellulose is the part is whitest. Yes, we are still performing some experiments, so those are the first steps of the project. That's all from my side. Thank you very much, and thanks to the organization for inviting me to this webinar.
Thank you very much for your presentation, Anna. I think it's very important that there are projects like ANIPH that aim to reduce the impact of plastics in such a complex humanitarian context. So thank you very much. And our final presentation, titled Development of High-Strength Biodegradable Stents, will be delivered by Yuan Chen. Yuan is a principal investigator in the Polymer, Recycling, Industrial, Sustainability and Manufacturing Group known as PRISM at the Technological University of Shannon, Mindless in Ireland. Her research focused on polymer synthesis, modification, processing, recycling, and biodegradation. She leads interdisciplinary projects and the interface of polymer science, bioeconomy, and circular manufacturing, developing advanced materials from renewable and waste biomass streams, including forestry and agricultural residues. In her presentation, she will address the development of high-strength biodegradable stents. These devices are a promising alternative to permanent metallic stents, as they can help reduce risks such as restenosis and chronic inflammation. To prove the mechanical strength of biodegradable polymers such as PLLA, her team has developed continuous iron wire reinforced PLLA filaments and new 3D printing platforms for the customized manufacturing of biodegradable stents, while reducing polymer degradation and material waste. So, Yuan, the floor is yours, and we can see your presentation in full mode.
Thanks very much. So, hi everyone. Our team is working on biodegradable corner stents. So, at the moment, drug-eluting stents is dominating this market. and but the research in fully bioresorbable stents still going on. And the main problem for, especially for polymeric biodegradable stents, is because the strength, because compared to metallic stents, they're not that strong. So lack of the radial strength, they tend to be thick, and because the thick, is everything okay?
Yeah.
Okay. So my goal is actually to reinforce, to make the material strong, so I can have a thinner stent strut. So one of the strategy is to have continuous wire as a reinforcement, and I made a crosshead die in simplified version, and installed onto our single screw extruder. So we have a wire coming one side and polymer come in from the feeding side of the screw, and when it's come out, it has this filament material outside and the iron wire inside. So with this material, we did the mechanical property test, and you can see that it's significantly improved. And that's where our material is compared to other published papers with metal wires. So this project is funded by Boston Scientific, it's a fellowship. So I had access to their mandrel, to their braiding machine. So using our continuous wire reinforced filament, we'll be able to make some stents, and we tested the radial strength of the stent as well. And you can see that the radial strength of the stents have been significantly improved. And we have a paper published on this topic, but the reason because by Boston Scientific's braiding machine and the mandrel, they're all kind of like a standard material. It's very expensive to make, and it's not able to achieve customized material, customized stents. So I moved on to 3D printing. I applied the same strategy to the printer head. So we have this needle installed here, basically to guide the wires coming, and then we print out with the wire inside. But we do notice the weak coming, the shortcoming is the wire is not in the center. But it's fine. We notice the weakness, but we just try to prove the concept, and we made some filaments. And I see if we can play. So we'll be able to print like these filaments have wires coming, and have material polymer filaments coming from the other side. You can see this wire, this is filament. So it be able to print like this, but because it's continuous wire, so we have to cut in the end. And no, it's fine now, just the concept. So after that, we did a degradation study, and and we found that actually have wire inside increased biodegradability. Those are images. You can see they corroded, but the problem, the thing is, we don't mind because we only use this to prove our concept. We can actually change to alloy or anything other materials, but that's not the point. The point is just prove the concept. And we have this paper published, and this is PhD students working on this. And after that, we moved on to 3D printing. So we changed our printing platform. We made this kind of rotating shaft, so we'll be able to print stents on this shaft. And those are the stents printed. Oh, I have image. We see it working. Okay. So this is kind of like a concept. Again, we have a wire coming and the element coming to the other side. We have to print out stents. So, and those are the image. Again, we do notice the material is not, some wires not in the center, like for example, this one. But anyway, that's something to be improved. And then I think yeah, this paper, this is published, and then we move on because as you can see, the 3D printing we use is FDM, and we have to use a filament. So the PLA filament, and if it's medical grade, it's expensive to make into filament, and it also have some issue with thermal stability. So we modified the 3D printer again, and we actually installed a single screw extruder instead of just feeding head, of the 3D printer. Okay, I can play this. So with this single screw extruder, you can put in the granule or powder of the polymer and then just print away. And we actually validate if this, we compare with the traditional non-modified FDM 3D printer with our modified 3D printer. We compare two of the printed samples, and there's no significant differences in mechanical properties. But we did prove that without step of making filaments, and the thermal degradation can be improved. And this paper was published in Additive Manufacturing. And then we move back to because we have this pellet 3D printer, so we just did another work about the recycling, because it's a granule or powder. So whatever you print it, if you don't need anymore or it's a failure or whatever, you can shred it into powder again. Or little particles, you can print it again, and we studied the mechanical property change, and this has been published in this paper. And then we move back to the 3D printing. Again, we put this single screw mini extruder, just printing the stents on the shaft. I see if I have video. Oh, I do. This is a video, so it's powder goes in, and just keep printing stent down the shaft. It's better, the performance is better than the other one, because the wire really interfere. So that's okay. So that's we recently published this paper, I think a few months ago. And we used iron particles as a reinforcement. And so that's our study so far, and we are working on new material rather than the commercial available material, because I still think they're not good enough. So that's my presentation. Thanks.
We have seen that plastics is a part of our everyday lives as a commodity, and I think it's quite innovative to start seeing it used in medical applications as well. So thank you very much for your presentation, Joan. Everything that you have explained to us today has been really, really interesting. I'm sorry to say that we don't have time to answer the questions that have been raised in the chat, but we will compile them and send you with the recording by email. Before closing the session, we would also like to remind you to follow us on our social media and visit the websites of ANIPH and MAGICBIOMAT projects to stay updated on our latest news, events, and results. Thank you very much to all of you for attending this webinar. I would like to let you know that the next webinar organized by ANIPH and MAGICBIOMAT projects will be in September. Thank you very much and see you soon. Bye.
Thank you. Thank you so much.
Bye. Thank you.
Thank you.
Bye. Thank you.
Thank you. Bye.
Thank you. Bye.